Hi, this is Project 21031, and we're the Bistatic Imaging Project sponsored by Rincon Research Corporation. My name is Cole Galloway, and I'm an electrical and computer engineer.
My name is Kevin Thompson, and I'm an electrical and computer engineer.
I'm Jeremiah Cunningham, and I'm an electrical and computer engineer.
My name's Joe Rye, and I'm an industrial engineer.
My name's Jake Livermore, and I'm a mechanical engineer. This is our design day poster, and our project goal is to create a portable system that can use signals of opportunity from local television stations to generate a two-dimensional map of the surrounding reflectors and transmitters. Now here's Joe with our project description.
The airways are flooded with various signals and transmissions radiating outward in every direction, bouncing off surfaces until they are either received by an antenna and interpreted, or until they dissipate. This project uses this property to image direct path and multipath reflections from an opportunistic emitter. By determining the directions of incoming reflected signals, the system constructs a two-dimensional image of the large reflectors in the surrounding area from a bird's eye view.
A coherent software-defined radio and a four-element antenna array with the RF front end operated atop the vehicle are used to receive these RF signals. Data is transmitted to a single-board computer where the beamforming algorithm is used to determine the angle of arrival. After being combined with the GPS and IMU sensor data, this information is used to determine the estimated latitude and longitude of where these signals originated from. The system then transmits this data to a laptop ground station that displays a two-dimensional image on a graphical user interface.
And as for the system, our antenna assembly consists of four elements in a uniform linear array. Our computer assembly has a GPS and IMU, which we gather data from to pinpoint locations on our two-dimensional map. We have the Jetson Nano, which is our single-board computer, and our Kerberos SDR, which receives the signals for processing. Our power assembly consists of a 14.8-volt lithium polymer battery, which is fed into different voltage regulators to feed the different components at 5 volts. Our software consists of direction-finding algorithms such as music, which is multiple signal classification, as well as location finding algorithms, which are, for example, is the Great Circle Model. A graphical user interface, or GUI, is a Java application to handle communication and displaying results.
And on the top right, we have an example of what our two-dimensional image will look like displayed on our graphical user interface.
This is our system block diagram. RF signals of opportunity, which are pre-existing signals floating around the airwaves, come from outside the system and are picked up by the four-element antenna array. Data is then sent to the SDR, and lines of communication are shown where the data is then sent to the Jetson Nano single-board computer to be processed, then sent to the ground station to be displayed as a two-dimensional image.
Now for the hardware of the project. The SDR we used was the Kerberos RTL SDR. This component is a combination of four RTL SDRs whose outputs have been combined into a single data stream. The reason that we chose this specific device was because of the extensive community around it, who have written sample code and libraries that were available for us to use. The single-board computer that we settled on using was the Jetson Nano by NVIDIA. This was our first choice due to the massive processing potential of the board GPU. Another advantage is that this SBC has I/O pins in the same configuration as similar boards like the Raspberry Pi. This allows us the use of modules and other sensors designed for those SBCs to be easily integrated into the system.
This is our antenna array. It's made of 3 rolling carts that slide along a linear rail via an accordion connector. The accordion connector separates each antenna at an equal spacing as it oscillates. The spacing between the first and last antenna correlates with half a wavelength of the signal being picked up. Our design was built keeping in mind the range of frequencies of local TV towers across Tucson, ranging from 450 to 609 megahertz.
Here, we are testing the data transfer between the ground station and our device. After establishing the connection, we calibrate the IMU, which collects magnetometer data in order to filter out hard and soft iron distortions, which are created by nearby objects and alterations in the existing magnetic field. This calibration results in a far more accurate heading data. After this, we go over to the Data tab, where we start collecting the latitude, longitude, orientation, and heading data from the GPS and the IMU sensor.
Here you can see the direction of arrival estimation and the demo software for the Kerberos SDR. At the moment, the program recognizes that the antenna elements are 1.8 meters apart and in the uniform linear array configuration. The demo software is using the music algorithm to estimate and display the direction of arrival of the target signal. At first, you can see the software is estimating the direction of arrival at 40 degrees. Since the array is in the linear configuration, the software sometimes gets confused and cannot determine the direction of arrival of 40 or minus 40 degrees, but quickly corrects itself. Later in the video, adjustments were made in the direction of the antenna array. The antenna was turned so that the incoming signal was perpendicular to the array elements. This is shown when the peak of the graph is at the 0 degree point. Here is the initial setup of the software. The Kerberos SDR must be calibrated before use, and the parameters being synchronized are the sample delay timings as well as the signal phase synchronization. The sample delay must be set because there are 4 SDR units within the Kerberos, and they all power up at different times. Synchronizing their sample delay ensures a coherent unit. As you can see here, the time delays of each of the internal SDRs is different, but then synchronizes to 0 at iteration 4. Once the program realizes the sample delay is synchronized, it switches focus to the phase difference. At iteration 9, the phase difference in each of the elements is 0, and the program can now turn off the noise source and begin graphing the estimated direction of arrival. The phase delays are calibrated with each of the antennas removed so that each individual element seen from the Kerberos is the exact same. Later, when the antennas are attached, the Kerberos will then be able to see the phase difference of incoming signals due to the spacing of each element. Calibration uses an internal coded noise source, which is turned off once everything is successfully synchronized. Once we start connecting the antenna elements to the Kerberos, you can see that the graph behaves erratically. The music algorithm is trying its best to make sense of the nonsensical data until all antennas are attached. This has no effect on the final data collection, however. Once all antennas are attached to the Kerberos, the plot becomes stable, and it can be seen that the estimated angle of arrival is approximately plus 40 degrees. In order to see if the direction of arrival could be manipulated indoors and detect other reflections, we decided to take a giant whiteboard and move it around the array. While the board is moved around the antenna elements, the plot changes and shows a distinct rise in the detection of an incoming signal around negative 55 degrees. This is approximately the angle at which the whiteboard rests with respect to the array when it is located to the left side of the array.
One of the concerns at the beginning of this project was that the reflected signals from the TV stations would be too weak to be able to pick up with a software-defined radio that only has 8 bits of resolution, which is why the low-noise amplifiers are built into our design as a precaution. But after initial testing, this turned out not to be an issue. In conclusion, the system we built is able to image direct path and multipath reflections. Furthermore, we built a custom antenna mount to easily change the antenna spacing, which helps with tuning to a specific frequency. We developed a graphical user interface to control the system and display results, and firmware that runs on a single board computer which handles all the processing, such as sample and phase syncing the software-defined radio, along with collecting GPS and IMU data which is used in calculating the estimated origin of these reflectors and transmitters. We are then able to communicate this data back to the graphical user interface over a static IP address.